A dam on a river is built so the wall facing the water is shaped like the region above the curve y equals 0.5x to the fourth, graphed here, and below the line y equals 160, graphed here. Distance is measured in meters. The water level is 30 meters below the top of the dam. Since 160 minus 30 equals 130, this is the water level here at y equals 130. So this shaded region is where the force is being applied. We want to find the force in newtons exerted on the dam by the water pressure. And we're given the density of water as well as the acceleration due to gravity. We can find the total hydrostatic force using this integral here, where we have the integral of w times d of y times L of y integrated with respect to y from a to b, where w would be the weight density, d of y would be the distance below the surface as a function of y, and L of y would be the width of the dam as a function of y. Before we set this up though, let's explain why this works. In general, hydrostatic force is equal to P times A, where P is the constant hydrostatic pressure and A would be the area. And P, the pressure, is equal to density times acceleration due to gravity times d, the distance below the surface. So because the distance below the surface will be changing, the pressure is changing, and therefore we'll have to use calculus techniques to find the total hydrostatic force. But we still use these formulas to set up the integral. The idea is that the total force applied to the dam would be approximately equal to the sum of the incremental forces at different values of y, where a sub I, the area, would be equal to L of y times delta y, where L of y again would be the width of the dam, and delta y would be the height of the rectangle. So if we take the limit as n approaches infinity of this sum, it gives us this integral here, where we have the integral of density times acceleration times d of y, the distance below the surface, times L of y, integrated with respect to y from c to d. Now I do want to mention in our textbook, they use w for this product here of density and acceleration due to gravity called weight density. Depending on what the problem gives you, you may have to find this product or they may give you the product. For example, if you're given the weight density of water is 62.4 pounds per cubic feet, they're already giving you rho times g. But in our example, we'll have to find this product. So going back to our example, let's begin by sketching a horizontal rectangle to help us set this up. So if we use this rectangle here, notice how the height would be delta y, which is why we integrate with respect to y. This distance here, this length, would be the distance below the surface, d of y. And this length here would be L of y. But let's begin by determining the weight density, or rho times g. The weight density W, or rho times g, would be equal to 1,000 kilograms per meters cubed times 9.8 meters per second squared, which would be 9,800. And these units would be newtons per meters cubed. And d of y, the distance below the surface, would be equal to 130 minus the y value, or just 130 minus y. Notice when y is 0, the distance below the surface would be at the very bottom, 130 meters below the surface. When y equals 70, the distance below the surface would be 130 minus 70, or 60 meters below the surface. And now to find L of y, the width of a rectangle, will be a little bit more challenging. Notice how from the y-axis to this end would be a length of x units, and from the y-axis to the left would also be x units. So this total length is 2x, but we need to write this length as a function of y. So if we know y equals 0.5x to the fourth, let's solve this for x. We would multiply both sides by 2. That would give us 2y equals x to the fourth. And now if we want x and we have x to the fourth, we would take the fourth root of both sides of the equation. So this gives us x equals plus or minus the fourth root of 2y. So then when it comes to the distance, this distance x is equal to the fourth root of 2y, and so is this distance here. And therefore the total distance, 2x, is equal to 2 times the fourth root of 2y. And therefore L of y, again, is equal to 2 times the fourth root of 2y, or just 2 times the fourth root of 2y. So now that we have the weight density, we have d of y, and we have L of y, we can now find the total force applied to the dam. The total force F is equal to the integral of 9,800 times d of y, 130 minus y, times L of y, which is 2 times the fourth root of 2y, integrated with respect to y from the bottom to the top of the water, or from 0 to 130. Now let's evaluate this on the next slide. Let's go ahead and factor out 9,800. Let's also factor out the 2. Now we can write the fourth root of 2y as 2 to the 1/4 times y to the 1/4. So let's also factor out 2 to the 1/4. And then we have the integral of 130 minus y. We still have y to the 1/4 here, so times y to the 1/4 integrated with respect to y. So we have 19,600 times 2 to the 1/4 times the integral of, this would be 130 y to the 1/4 minus y to the 5/4. Now we'll find the antiderivative. So we have 130 times the antiderivative of y to the 1/4 would be y to the 5/4 divided by 5/4. Instead of dividing that, we'll multiply by 4/5. So times 4/5 y to the 5/4 minus the antiderivative of y to the 5/4 would be y to the 9/4 divided by 9/4, or 4/9, the reciprocal, times y to the 9/4. Now we'll perform the substitutions. Well, 130 times 4/5 works out to 104. Notice how there's 1, 5, and 5, and 26 5s and 130. So when y is 130, we have 104 times 130 to the 5/4 minus 4/9 times 130 to the 9/4. And then when y is 0, notice both terms would be 0. So now we'll go to the calculator and get our decimal approximation. So we have 19,600 times 2 raised to the power of 1/4 times 104 times 130 raised to the power of 5/4 minus 4/9 times 130 raised to the power of 9/4. So we have 472,926,425.8, and this would be newtons. This is the force being applied to the dam, and this would be newtons. I hope you found this helpful.